Hi, my name is Mario Emilio Mendez Gonzalez, and this is my second evidence. So let's start off by what is a discrete time-state-space model and how does it differ from a continuous time-state-space model. So this model is the one that provides the same type of linear difference relationship between the inputs and outputs as the linear AR max model, but it's rearranged such that there is only one delay expression contrary to a continuous time-space model. In the discrete model, you cannot use continuous time frequency domain data. What is meant by state feedback with observer? This second concept we will review is the state feedback. The state feedback corresponds to using values of the state variables. These variables can fully describe our system. In some cases, some variables are unable to be read, and this makes the feedback not possible. So that's why we can design an observer to generate replicas of the system and use the variables of this replica to implement the feedback. What is the procedure and which MATLAB functions are used when designing a state feedback controller with observer? So our procedure in the MATLAB software was by using the resources from the last evidence, we adapt our best model into this new feedback code. We use controllable canonical forms, state feedback gains, and observer gains with these first pulse coordinates of our model. This helps to observe the closed loop system, and output disturbance is already included as an input in addition to reference signal. So basically what we did here was export our best model from the ARX model code from MATLAB as well, and find the coordinates of our poles. Once we got the coordinates of our poles, what we are meant to do is to look how the poles are distributed around the circle and make them be and move them to be as close as they could be to the center. We use all these, and we use the canonical forms. We use this is the part of the code where we put the coordinates of our poles, and also with the Laplace with this code, what we did was to start like the procedure to get a graph. How should the closed loop poles be chosen when working with discrete time systems? So this is the map we get with our first poles. So the poles we want to use should be the ones that are closer to the center of our figure. The closer, the better. Also, we have to take in the count the desired speed and damping. In this figure, we can see two poles that are right on the border of the circle. These poles are the ones we are interested in. So we are interested in these poles because they might cause a really unstable system. So all these poles zeros, we want to make them as close as we can to the center. And well, this is the pole zero map from the first poles from the first coordinates of the poles we use. So for our final choice of poles and results, so to this is the how the final pole zero map. To approach these poles to the origin of our circle, we use the PO line of code to make to power our coordinates of our poles to the 7. This makes them to be closer to the center, and well, using the absolute number of poles, we can know which poles modify. That by modifying the poles, which absolute number approach 1. Once done that, we got this pole zero map with the following modified poles. So we use this line of the code that was implemented by myself. So what we did was find the absolute number of this PDS where we put the coordinates of our 14 poles. We use them, and we got the results from a range of 0 to 1. The ones that were closer to 1, we needed to make them less. So that's why. So I find out that the bigger absolutes were in the coordinate 9 and 10. This one. This is already the final model. This is already the final pulse we'll be using. So we do that. So in our dot plot, we get as a smooth down movement of the graph, because before we modified the pulse, we had a big spike right here, and as well as here there were a lot of waves that represent instability. But with these pulse coordinates, once modified, as we can see, we actually managed to get a really fast responding system, and a really stable one. So this is what we get. This is from our step response. So this is as close as I could get, because I got an error if I try to move the pulse a little bit more. So I just stopped there. I think this is the best I could get. So yeah, that's it. So also conclude by sharing what you feel is the most valuable knowledge you have gained in this course. So learning these features that can be applied into advanced technology is always a good topic. Adapting our knowledge to perform in today's professional life is key. Without a doubt, the ARX models were as challenging and as fun to calculate and simulate. This part was all about playing with our results and getting as much accurate to a desired simulation. During these 10 weeks, this topic and this class in general has been a real challenge, and also a good way to practice my knowledge in design control. I am grateful for the knowledge I acquired and good exercise and preparation for my professional life. So that's it, and thank you.